Welcome to the third and final video of the complex arctangent series. I'm Daniil, your teacher, and we're going to be looking at complex arguments again. Basically, we're going to do the same thing we did last video, but with r greater than 1, and you'll see just how big the difference is. And finally, you'll see why I mentioned at the start of the video, at the start of the series, I analyzed the arctangent of re to the I theta itself, and I showed you that there was obviously an issue at r equals 1. So now you'll see what has changed from r less than 1 to r greater than 1. That's all I have to say. Let's go. So we're going to start the same way we did before. We're going to consider that the imaginary part of this particular complex logarithm is just the argument of the inside. And then we're going to integrate both sides from minus pi over 2 to pi over 2 because they're equal. And again, I chose that range because that keeps theta, or that keeps arctangent within its range. And yeah, I thought that was a natural choice. Anyway, so for the left side, we have this. Okay, and remember the trick we used to shift the bounds, get rid of that I. Okay, now, if you remember in the last video, we used a series expansion immediately for this logarithm, but the issue is r is greater than 1, so here we're just not allowed to do that. Before r was less than 1, so we are. So now what we're going to do is we're going to split this. I'm going to pull the imaginary part outside. We're going to rewrite this as the logarithm of minus re to the I theta plus the log of 1 minus 1 over r e to the minus I theta. You can check that this was equivalent. All I did is just factor out a minus I r e to the I theta. Now you see that this term has a 1 over r as its modulus, which you know has to be less than 1 if r is greater than 1. So that means we're going to be able to expand this with the series. But first, let's tackle this. So imaginary part's going to carry in here. We want the imaginary part of this. Now, here's what not to do. I'm going to put a question mark. Why can't we just go, this is equal to log minus 1 plus log r plus log e I theta. Okay, so following this process, you know log of minus 1 is I pi, log r is just log r, and then this is I theta. So from there, you would deduce that the imaginary part is theta plus pi. That's what you would get if you follow this natural path, because you want to take the imaginary part, and this is the imaginary part of that. But this process is wrong. What's actually the case is that you know that the imaginary part of a complex logarithm is the argument of the inside. So you have to ask yourself, is this the argument of the inside? No, it's not. The argument has to be from minus pi to pi. But if you look how theta is defined, this is in pi to 2 pi, right? So basically, what we need to do is we need an angle that is effectively the same as this, but that falls into minus pi pi. So let me make this clear. This is in pi to 2 pi. So how can we get this into minus pi pi? Well, how do you change an angle? Or sorry, how can you shift an angle but keep it the same angle? Well, by 2 pi. So naturally we should subtract 2 pi to still get the same angle, but this will put us in minus pi 0, because what this ends up being is just theta minus pi. With theta defined from 0 to pi, you have this in minus pi to 0, which is allowed by rules of the argument's principal value. So yeah, basically you could, that's a major pitfall. You could have accidentally put theta plus pi instead of theta minus pi, but you got to remember, the imaginary part of the logarithm is the argument. You can't just split go willy-nilly. I haven't done enough research into it, but maybe there's some way to justify it in that you know that minus 1 isn't just e to the I pi, but it's also e to the minus I pi, or e to the I minus pi. So maybe there's some way to directly get the minus pi without having to do the mental gymnastics, but whatever. So what we end up having is, for the first part, we just have the theta minus pi, and then we have plus the imaginary part of the other integral, which was this logarithm. Okay, this we can easily integrate. This is just going to be pi squared over 2 minus pi squared, which is just minus pi squared over 2. Okay, nice. And then here we can just use our series expansion. So remember, well, I'll just write it explicitly here, since we know 1 over r is less than 1. It's that. So let's plug that in. It's going to equal minus pi squared over 2 minus sum. Again, I'm going to exchange the summation and the integration without justification. As usual, you know the drill. That was a bar, by the way. So everything only dependent on k can come out. And then we have the integral e to the minus ik theta. Yes. And then, oh, imaginary part. But we can just remove this imaginary part. Because it's linear. Everything here is linear. Get a minus sine k theta. Which removes our negative out here. And you know that this integral is just other way around. This is 1 minus 1 to the k over k, just integrals. So in fact, notice that when we multiply this in here, we can just write this using dilogarithm notation again. This first term will be the dilogarithm of 1 over r. Second one will be dilogarithm of minus 1 over r. So this equals that. Okay, so let's restate this with an integral on the right side as well. So we have minus, oh wait, no, we can do this up here. Minus pi squared over 2 plus dialog 1 over r minus dialog minus 1 over r. It's bad r. Equals the integral from minus pi over 2 to pi over 2 of the argument 1 minus IR e to the I theta. Yeah. Okay. So now, what we did before is we just rewrote the argument in terms of an arctangent, and all was fine and dandy. We didn't have to worry about anything, but here we actually will. So let's see what happens when we consider the same sort of arctangent term. So remember, we typically use arctangent imaginary part over real part. So that means the argument, I'll put a question mark. Is it just the same as before? Arctangent minus r cosine theta, which is the imaginary part, over the real part, 1 plus r sine theta? Answer is no. With r greater than 1 here, we have an issue in that this has a sign change, 1 plus r sine theta, because there's a point where it equals 0 on the inside, and in fact, this, which represents the real part, can become negative. Now, let's see what happens when the real part's negative. So, with theta in minus pi over 2 to pi over 2, the imaginary part, which is the numerator, is only negative because cosine theta is always positive. So we're only working in the bottom half of the complex plane. So let's see what's going on. Now let's think, what is it? When the real part is negative, which we know is possible. Like for example, just take theta is minus pi over 2, right? This is just 1 minus r, straight up negative, as shown here. So let's consider some complex number z, and this would be its argument. Its argument would be something negative. So remember, we're only dealing with negative imaginary part. We're only dealing with negative imaginary part, and now we're assuming it has negative real part. So with a negative real part, if you think about it, this is what arctangent's doing. So if this is the argument, you can already tell that this has magnitude greater than pi over 2. So you know that arctangent isn't doing its proper job to represent the argument, because arctangent can only give us from minus pi over 2 to pi over 2. But this angle has magnitude greater than pi over 2. So the reasoning for that is that, like, basically when it comes down to it, arctangent of minus y over minus x is the same as arctangent of y over x, if you think of like y as imaginary part, x as real part. So arctangent's dumb. It doesn't know the difference between a negative over a negative and a positive over a positive when you're dealing with arguments. So the arctangent will equate the minus imaginary part and the minus real part with positives for both. So arctangent will spit out this angle, which is wrong. But what you can do is you can tell that these are obviously separated by an angle of pi. So clearly the true argument is basically what we get from the arctangent minus pi. But this only holds when the real part is less than 0. So what we do is we can just say this has to be minus pi. This is only when 1 plus r sine theta less than 0, but we can be more specific. This just means, we know that, for example, for minus pi over 2, that this will be negative, so we know that's like the bottom bound. So if you just solve this equation equal to 0, you know that theta has to be in this range. When theta is in this range, this is the same thing as r being negative. Maybe I need to do this. It doesn't really matter, it's an integral. So now we have an actual theta range for where this pi will appear and when it won't. So now we have an expression, a full expression for the argument, so let's plug that in. So this is the same thing as, of our arctangent, which after pulling out a minus is this. And then minus integral from minus pi over 2. So remember, it's like this bonus term is 0 outside of that range I mentioned, but here we'll have a pi. D theta. And this is just going to be arc sine 1 over r minus pi squared over 2. And wow, would you look at that? Constants cancel. So once you do some rearranging, you can get the integral formula for the same integral we did before, just with a different a set of r values. So we have the integral from minus pi over 2 to pi over 2 for arctangent r cosine theta over 1 plus r sine theta equals, like I said, after the rearranging and the removing the negative, so the positive term is now the one with the minus. And this is your new formula. So it's the same integral as before, but with a different domain. So it is technically new. And now, as you see, there is a lot of nuance when you're dealing with the argument and stuff that, for example, real parts that have sign changes, or any parts that have sign changes, you got to watch out for those. And now, as you see that when we analyzed just arctangent RE to the I theta itself in the start of the first video, you can see that that little issue at r equals 1 propagated all the way into analysis of its, constituent parts of like the logarithms. So yeah, I thought that was pretty cool. If you thought it was cool, let me know. Yeah, series is done.